Welcome to KCSE Physics Paper 1 of the year 2025, the complete marking scheme. And let's go to the first question. In this question, you're told that a micrometer screw gauge with an error of positive 0.02 millimeters shows a reading of 0.31 millimeters when used to measure the diameter of a steel ball. Determine the actual diameter of this steel ball. This is a very simple question because for you to determine the actual diameter, you need this equation here. Actual diameter is equal to the scale, a reading, which is given, minus the zero error. And you can see since the zero error is positive, minus and positive gives you minus. And when you manipulate this, you get 0.29 millimeters. Let's go to question number 2. In question 2, we are given that students want to cut down a tree without destroying any of the houses around it. Describe how the students can estimate the height of the tree using the height of one student to safely cut down the tree. Again, this is a very simple question because it comes from use of this equation here. The height of the student determined by the height of the tree will be given by the length of the student's shadow divided by the length of the shadow of the tree. So the student can use a tape measure to determine the height of the student and the length of the student's shadow and that of the tree. Okay, these are the three measurements that the students can take: the height of the student, the length of his or her shadow, and then the length of the shadow of the tree, and then substitute those values into this equation and they will have comfortably estimated the height of the tree. Let's go to question 3. In question 3, we are told that figure 1 shows a building block placed on a plank of wood supported by 2 pivots. There is this plank of wood, there are these two pivots, and then there is a block over here, plank of wood. Now, on the diagram, show how the tension force acting on the plank of the wood. How do we show tension here? Of course, the tension is supposed to be shown by 2 arrows which are pointing towards each other because this plank of wood is being stretched. If you find this a bit challenging, then consider a situation where you have the 2 planks but you've got a rope or a thread connected between the 2 supports. The type of force which exists in the string is called tension, represented by the letter T. These 2 arrows will be pointing towards each other. What is the meaning of this arrow? It means that this string is pulling this support in this direction. What does this T mean? This T means that the force in the string is pulling this support in this direction. Now, if we put an object at the center of this string or just pull the string downwards, the tensions will look like this. Okay, they will look like this because it means that this string is pulling this point in this direction, while this part of the string is pulling this point in this direction. We can compare that plank of wood to this string here because it is under tension and the forces which are acting on it by these 2 arrows, because we want to show the forces which are acting on, which are exerted by this string at this point. Similarly, we want to show the amount of force which is exerted by this plank at this point, because the force which tends to make this plank to sag acts at this point. So we want to show how the force exerted by this plank at this point acts. We want to determine the direction, and it can only be in this direction. So that is how we show tension in an object which has been stretched. Tension in an object which has been stretched is shown by two arrows pointing away from each other. Okay? This object here has been stretched. These two arrows pointing away from each other. All right? And that is how you get the answer to question 3. Let's navigate to question 4. Now, in question 4, we are told that figure 2 shows a person squeezing a tube of toothpaste. All right? And then we are asked to state the principle that is applied in squeezing the toothpaste out of the tube. Of course, this is Pascal's principle. Okay? Pascal's principle. So, but we have been asked to state the principle. Okay? So, other than knowing that it is Pascal principle or the principle of transmission of pressure in liquids, it is important to state it. So, pressure exerted at one point in an enclosed liquid is transmitted equally to all other parts of the liquid. That is how you state the principle of transmission of pressure in liquids, or Pascal's principle. Let's go to question 5. Question 5. In question 5, we are given that in a certain experiment, 2 centimeters cubed of dry salt is dissolved in 10 centimeters cubed of water. It was observed that the volume of the salt solution was 10.5 centimeters cubed. Explain why the volume of the solution was not the same as the sum of the individual substances, because we would have expected 2 centimeters cubed plus 10 centimeters cubed to give us 12 centimeters cubed. But we have seen that when we add 2 centimeters cubed of salt to 10 centimeters cubed of water, we gain 10.5 centimeters cubed of solution. Okay? This is because the particles of the solute, which is salt, it goes and fills up the intermolecular spaces between the molecules of water, right? So the particles of salt, being smaller than the particles of water, filled in the empty spaces between the water molecules. At this point, I'd like to point out that it will not be correct for you to say that it fills in the air spaces. It's not the air spaces. Those spaces are empty. They do not have any solid matter. Okay? They are not air spaces. The intermolecular spaces of water are not air spaces. They are just empty spaces. Question number 6. Let's see what we have in question number 6. In question number 6, we are given, state one feature of a clinical thermometer that allows the reading the reading to remain constant when the thermometer is no longer in contact with the body of the patient. Okay? And this is about the constriction. The constriction which is located just beyond the bulb. Just to emphasize this, I've cropped up these from your course book, and you can be able to go to the course book and read how that happens. So this is the constriction. Okay, that is how this feature, the presence of the constriction, helps the nurses to read the temperature even when the bulb is not in contact with the patient. Right? You can read all this literature and it will give you the correct answer. Let's navigate to question 7. Question 7. Figure 3 shows 2 spanners that can be used to loosen a nut. So there is one with a shorter handle and there is another one with a longer handle. Okay, explain why the spanner B, the one with the longer handle, requires less force to loosen the nut. Of course, this is about factors affecting moment of a force about a point, and one of them is the magnitude of the force. But these two forces may be the same, but you find that over here you can apply a smaller amount of force to produce the same turning effect as the larger force applied here to produce this turning effect. When we want to loosen, there is a certain minimum torque that is required. Okay, torque, or the turning effect of that force, which is the force times the distance. These are the two factors which affect moment of a force about that point. In order to produce that torque, there is a certain amount of force that you have to apply if this is the length. To produce the same amount of torque, you can use a smaller force but then increase this distance. So it is much easier to use this, because when we compare the perpendicular distance from the turning point all the way to the line of action of the force, here it is larger. All right? So a possible answer would read like this: the perpendicular distance from the turning point or the nut to the line of action of the force. This is the line of action of the force, okay? And this is the perpendicular distance from that point all the way to the line of action of the force. Is larger, in B, it is larger. Hence, it increases the moment due to the force. This allows a smaller force to be used to produce the required moment. Okay, you can use a smaller force to produce the required torque. And that is how you would answer question 7. Let's go to question 8. Question 8 is about equilibrium and center of gravity. Figure 4 shows an oval ball balanced on the ground. This one here. Explain why the ball is said to be in unstable equilibrium. So the state of equilibrium has already been identified for us. It is unstable. Why is it unstable? We are asked to explain why. So you should know why objects which are in unstable equilibrium behave that way. Okay? So it's about pushing this object slightly or displacing this object slightly by pushing this end. When we push this end slightly, we find that there is this point here, which is the center of gravity of this oval ball. Okay? It looks like a rugby ball, right? Or like an egg, right? So its center of gravity is at this point. There is this vertical line from the center of gravity. It passes through this very small area. So a slight push of this object, maybe in this direction, will make that vertical line from the center of gravity to fall outside the base support. When that happens, if you release this object, there will be moment due to that weight about this point, and that moment will make the object to fall away from the new position. So it will not remain in that new position, it will fall further away. Right? So here I've drawn the same diagram just to assist you to see this. But before I give you that diagram, let's realize that, okay, this one is found from your course book, this textbook, this diagram here. In your textbook, we use a cone. When it is put on in its sharp end where the area is very small, a slight push will make this vertical line from the center of gravity to fall outside the base support, this short base support. So when it is released, there will be clockwise moment about this point, and that moment is to make the object fall away from this new position. So What is the explanation? A small sideways push can cause the vertical line from the center of gravity to fall outside the base. The moment due to the weight about this point causes the cone to tip, or causes this object to tip, because it's not a cone. So in your explanation, you will be referring to this ball. It causes the ball to tip. Let's see whether if we displace this sideways, let's see what we are going to get before I explain the second point that you could have used to explain why this object is in unstable equilibrium. This is the second diagram here. So like I told you, the first diagram, the vertical line from the center of gravity acts through the base support. In the second diagram, that vertical line falls outside the base support, just like in this cone. And therefore, when this ball is released, it will fall clockwise, because there will be net or resultant clockwise moment about this point, making the ball to fall away from that point. The second way in which you would have explained why this ball is in a state of unstable equilibrium is with respect to the position of the center of gravity. This is the position of the center of gravity when it is in this shape or in this position. The center of gravity has got this height. But when slightly displaced, the position of the center of gravity is going to be lowered. So the object is more stable in this new position than in this position. So when it is released, there is no way it can move from a position of greater stability to a position of less stability. You should realize that here it is less stable because the position of its center of gravity is higher than in this position. So it is more stable in its new position. When released, there is no way it can move back to its position of less stability. So it will fall further away in order to lower this position of the COG further until it is lying on this surface, where the position of the COG will be as low as possible from this reference point. So those are the 2 points that you would have used. But probably the one that you saw is the vertical line falling outside the base support. If you saw this other one whereby the position of its COG is lowered, then there was no problem in your answer. Let's look at question 9. Question 9. In question 9, we are given that a student is required to calibrate a spring balance for use in measuring the weight of an object. Other than the spring and the masses, name one other apparatus that the student must have in order to calibrate the spring. What other apparatus must the student have? The student can have a graph paper strip or a millimeter scale, or from a meter rule probably, because this is how you calibrate the spring, right? We've been told the spring is provided, the weights are provided, so probably you might require this graph paper here in order to mark the various positions of the pointer as you add the weights, because you will adjust this mark until it is lined with one of the marks, and then mark that point 0 when there is no weight on the hook. Then you put a weight of 100 grams, which is 1 Newton. Then you are going to mark that particular position and call it 1 Newton. Then you put 2 Newtons. You go to the next point, you mark 2, and so forth until you've got several marks on this strip of graph paper. So probably the other material or apparatus that you might need was a strip of paper. In question 10, it is observed that a vehicle travels on a dusty road, leaves a trail of dust rising high above the ground, explain this observation. Of course, this question comes from fluid flow, and it's about turbulence. So probably you might give an answer like this one. Due to the shape of the car, the lines of flow of air behind the car are not streamlined. The flow is turbulent. The low pressure pulls air particles into the space behind the car, and that is why it appears dusty. Probably that is the kind of answer you can give for question 10. About question 11. In question 11, we are given that an object moving with an initial velocity of 3 meters per second is uniformly decelerated to a stop after moving through a distance of 10 meters. Determine its acceleration. This one comes from linear motion, and it would be expected that you can list down all the physical quantities given in this question. I usually recommend that students use an acronym referred to as SUVAT. S-U-V-A-T, SUVAT. So the moment you write SUVAT, S is displacement, U is the initial velocity, V is final velocity, A is acceleration, and T is the time. These are the physical quantities which are found in the three equations of uniformly accelerated motion. Then we are required to calculate the acceleration. So this is a requirement. But remember that we do not know t, so we avoid an equation that has t, and that is why we settle for the third equation, and by substituting there we get the acceleration to be minus 0.45 meters per second squared. Remember, we've been asked to find the acceleration, so there is no need of calling it deceleration. But if you had been asked to calculate deceleration, then you would say deceleration is equals to 0.45 meters per second squared. In that case, you will not include the negative. So this question was very easy. Let's navigate to question 12. A student placed a coin on a smooth cardboard, which was on top of an empty glass beaker. The cardboard was then suddenly pulled horizontally away from the beaker. State and explain the observation made. So in this marking scheme, I've tried to provide you with this diagram because this diagram describes exactly what is happening here. So I've also included a simulation so that you can be able to see what is happening, and that will cement this kind of demonstration in your mind. So let's play the simulation and see what happens. So if I click, you will see that's exactly what happens. Let's repeat that again. Let's play the simulation. When we push this card away, we find that the coin falls to the bottom of the tumbler. It takes the same amount of time for this object to hit the ground as the coin. So I have deliberately slowed it down so that we can be able to see that the moment this one lands, it is the same time the coin takes to hit the bottom of the tumbler. All right? So how do we explain that? This is about inertia. It's about Newton's first law of motion. So this coin had a tendency to remain at rest. So when this card was suddenly pushed horizontally, there was no time for the resistance between the coin and the cardboard to act. So since there was no horizontal force, then this coin could not be able to move. It's got a tendency to remain where it was, all right? And that is why it remained there, but then there was no other force holding it in that position, so it fell to the bottom. So what is expected? The observation was that the coin fell into the glass. It's just as simple as that. You get 1 mark for that. For the explanation, you get 2 marks. The coin had a tendency to remain at rest, or you could say the coin had inertia, since it was initially at rest. It therefore fell under gravity when the card was removed. It must fall under gravity, because we can do this same experiment with the card resting on top of the table with the coin on top of it. If we flick that card away, the coin remains in the same position. Okay, but in this case, the coin fell into the glass. Right? The coin fell into the glass. So you must explain that this coin fell under gravity. All right? Here it had inertia, so it remained in the same position. But since there was no force still holding it in that position, there was no upward force holding it in that position, then it fell under gravity. So it accelerated vertically downwards. Let's move over to question 13. Question 13. State one source of non-renewable energy. In your course book, you've been given a list of renewable and non-renewable sources of energy, which include firewood, charcoal, coal, alcohol, petroleum, biogas, and nuclear energy. These are non-renewable sources, and they just wanted one source, just one, for 1 mark. So it is important to recall examples of non-renewable sources of energy as well as examples of renewable sources of energy. Let's navigate to question 14. Question 14. Explain why a person trapped inside a smoke-filled room is advised to crawl along the floor towards the exit. From which topic does this question come from? It is from heat transfer. Heat transfer. By the way, as we come to the end of section A, there is a document that I've prepared, and you can get it if you are a member of this channel. And you can see that when I hover the cursor over each question, it gives me the topic from which that question comes from. You'll be able to see that particular topic. It is written there. So when you're using this document for revision, then this document can be quite useful. So go ahead and download it, and you can be able to use it in your work. So let's go through question 14. Explain why this person in a smoke-filled room is advised to crawl along the floor towards the exit. Cold, fresh air, being denser than warm, smoky air, is found near the floor. You know, in order not to choke, you want to expose yourself to fresh air. Okay? So, and we know denser gases are found as low as possible, so they will be found closer to the floor. Okay? But warm, smoky air is found floating on cold, denser air. So that is why this person would encounter cold, fresh air near the floor than when the person is just standing. So let's go to section B, and in section B we've got question 15. Question 15. State the meaning of the term specific heat capacity. So probably in this question you are being asked to define specific heat capacity. It is the quantity of heat required to raise the temperature of unit mass of the substance by 1 degree Celsius. For example, when you are given the specific capacity of water as 4200 joules per kilogram per Kelvin, that would mean that the quantity of heat required to raise the temperature of 1 kilogram of water by 1 degree Celsius will be 4200 joules. So let's look at question 15b, part 1. We are given that a student observed that when an ice cube is placed in water, it melts. Explain this observation. Of course, this one is very simple. When you compare the temperature of water and the temperature of ice, probably the water is at 20 degrees Celsius, the ice is at 0 degrees Celsius, so heat will be transferred from the water to the ice. Okay, so when the ice gains heat, it's going to change state, okay, because we are assuming that ice is at 0 degrees Celsius. But remember, we can have ice at a temperature lower than 0. We don't need to always use ice at 0 degrees Celsius. We can have ice at minus 10 degrees Celsius, for example. In such a case, when such a cube of ice at minus 10 absorbs heat, the first thing that will happen is that its temperature will rise, okay, until it reaches 0 degrees Celsius. But in this case, we are just assuming that the ice is at 0 degrees Celsius, so the temperature of the ice is higher than that of water, so definitely water will lose heat to the ice, which will melt to form water at 0 degrees Celsius. State ways in which the melting point of the ice could be reduced. We know that factors which affect the melting point of a substance could be things like impurities, all right? So we would pour a certain amount of impurity, for example, salt, on the ice. It's going to melt at a temperature which is lower than 0 degrees Celsius. It can melt at 2 degrees Celsius if we were to pour salt or sand on it, because salt or sand, they act as impurities, and impurities tend to lower the melting point of a substance. In this case, it is ice. The other thing that we would do is that we can apply pressure. We can apply pressure on the ice. So those are the two factors which affect the melting point of ice. So pour an impurity such as salt or ice, salt or sand on the ice. Number 2, apply pressure to the ice. It will melt at a temperature lower than 0 degrees Celsius. Let's go over to part C of question 15. And in part C, we are given that a block of ice at 0 degrees Celsius is supplied with the 2000 joules of heat. Determine the mass of the water that will melt. Okay, so we know the quantity of heat, we know the specific latent heat of fusion of ice, which is 3.36. So by using the equation Q is equals to mLV, heat absorbed is equals to mLV. So we've got 2000 joules equal to the mass of the ice which melts times its specific latent heat of fusion, and that gives us 5.952 by 10 raised to minus 3 kilograms, or 5.952 grams of ice. D. A student mixed 25 grams of hot water at 50 degrees Celsius with 75 grams of cold water at 20 degrees Celsius. Determine the final temperature of the mixture. Okay, this is the method of mixtures. So the water at 50 degrees Celsius, will lose heat to the water at 20 degrees Celsius, and the quantity of heat lost by hot water is equal to the quantity of heat gained by cold water when we assume that no heat is lost to the surrounding. And here by using that expression, heat lost by hot water is given by mc delta theta. mc delta theta. M is the mass of the hot water. This is the specific capacity of water. And this is the change in temperature of the hot water. Remember, the final temperature of the solution will be theta. So theta is lower than 50. But when it comes to the cold water, heat gained by cold water, its temperature is going to rise from 20 degrees Celsius all the way to theta. So the change in temperature is theta minus 20. So this is 50 minus theta, but here it is theta minus 20. I've already explained how that happens. So probably you can see that the specific capacity of water cancels out with the specific capacity of water here, and we have this expression. And finally, by solving this expression, you can be able to get this particular expression. Okay, I did not finish it. By solving this particular expression, you can be able to get the final temperature, which is theta. In this particular question, you may have noticed that the value of the specific capacity of water provided was not correct. This is 42,000, but the specific capacity of water is supposed to be 4,200. 4,200. It's not 42,000. But even if you were to use that value, you will get the same value as the person who used the correct value of the specific capacity, because specific capacity cancels out from both sides of the equation. Yeah, in such a case where you find that the details provided in the question, they are not correct, you've got two options. Here you can go ahead and use this wrong value as provided. Your answers will simply be correct because they've told you that take the specific capacity of water to be this value. Okay? Specific capacity of water to be this value. The other option is for you to use the correct value. The correct value, because we know it is 4,200. If you use the correct value of the specific capacity, again, the answer, they will mark your work according to how you have substituted in values. So there is no need to panic when you find that wrong values have been provided. So let's go over to question 16. Question 16. A student of a certain school wants to verify Boyle's law. State two apparatus that the student will need. Boyle's law. Of course, for you to be able to verify Boyle's law, you will need this thick walled glass tubing. You will need a millimeter scale, somewhere around there. Need a millimeter scale. You will need a Bourdon gauge to be able to measure pressure. And you might need a foot pump for you to be able to increase the pressure on this side of the U-tube so that it can squeeze this gas here. All right. So any one of these apparatus, any two of them, the pressure gauge or the Bourdon gauge, in order to be able to measure pressure, thick walled glass tube, foot pump would be required, and then a millimeter scale in order to be able to determine the volume of the gas enclosed here. Part 2, we were asked to state one quantity that they would keep constant while verifying Boyle's law. Of course, it is the temperature of the gas. Temperature of the gas. How that one is done is not asked, but it pays when you are revising to know how that is achieved. Let's go to the next part of question 16. B. Figure 5 shows an apparatus that was used to investigate the rate of diffusion of two gases A and B, which form a white deposit when they interact. There's a white deposit here. There was gas B, gas A, and you can find that the white deposit was formed closer to gas B. So the gas that diffuses faster is the one which covers a longer distance in the same amount of time. So identify the gas that diffused faster. That is gas A. Gas A. State two ways of increasing the rate of diffusion of the two gases in the tube. Of course, one of the ways of increasing the rate of diffusion is to perform this experiment at a higher temperature. To perform this experiment at higher temperature, right? Or to heat the gases. That is one of the ways. Okay. Another way would be to increase the concentration of the gases, right? So you can state any two factors. Raise the temperature of the gas, because this is 1S here. Raise the temperature of the gas. And number two, increase the concentration of the gases. Let's look at part C of question 16. Part C has got part 1, explain Charles' law using the kinetic theory of gases. So it calls us to know what Charles' law states. Okay? What does that Charles' law states? It states that the volume of a fixed mass of a gas is directly proportional to its thermodynamic temperature. In other words, if you double the thermodynamic temperature of the gas, you're going to double the volume at constant pressure. So it's that law that we've been asked to explain using kinetic theory. How do we do that? I've written a number of points here which you can pick several of them so long as they follow each other well. For example, I've already mentioned that when the temperature of a gas is increased, the kinetic energy increases. The kinetic energy increases. And when the kinetic energy of the gas increases, it means that the particles are going to move faster. So this increases the speed of the particles. If the speed of the particles increases, the rate of change of momentum, which is force, increases, leading to increase in pressure. Okay? This would happen if the volume of the gas does not change. Okay? The pressure will increase if the volume of the gas does not increase. Since Charles' law requires that the pressure of the gas be constant, then the volume of the gas must increase, so that although molecules are moving faster, the number of collisions per unit time must be reduced, since the distance between the walls is increased. Like I said, you have to pick a number of points from this. So it pays to know how the kinetic theory can be used to explain the other two laws, Boyle's law and pressure law, because any one of them could be picked. This one over here is a calculation. The volume of a fixed mass of a gas is 20 centimeters cubed. So this is V1. At a temperature of 19 degrees Celsius, it will be expected you change this to Kelvin by adding 273. Determine the volume of the same mass of the gas when the temperature increases to 24 degrees Celsius. Again, you change this temperature to Kelvin, again by adding 273 to it. So we are going to use the equation V1 over T1 is equals to V2 over T2. And if we substitute, we get V1 over T1 is equals to V2 over T2. Again, you can solve this particular equation to get the new volume of the gas. Let's look at question 17. In question 17a, we are given that figure 6 shows an object moving at a uniform speed on a circular path or in a circular path of radius r. Given that the object moves from point A to point B in a time t seconds, I guess there was some kind of typing error here. It must have been from point A to point B in a time t seconds. Okay. Part 1 of A, this part here, we are asked to indicate on the diagram the angular displacement. It's moving from point A to point B. The angular displacement is this one here, while the linear displacement is from point A to point B. So we are going to indicate theta at this point and s at that point, because this is the linear displacement. This arc length is s, while this angle here is theta. All right, let's move over to part 2 of A. Part 2 of A, again, it's got two parts. One, we are asked, write down an expression of the angular velocity omega in terms of t, because omega is equals to theta over t, because it is the rate of change of angular displacement. So this is the expression. Okay, and then the next one is to derive an expression for the linear velocity v in terms of angular velocity. So we start by defining linear velocity, which is the linear displacement divided by t. But we know from the definition of theta that theta is the ratio of the angular displacement to the radius, and when you make linear displacement to be the subject, you get s is r theta. Of course, this is t. When you separate these variables, you get r times theta over t, but theta over t is omega from this part. It's omega, so v becomes equal to r omega. So in these topics, you must get used to the idea of deriving simple expressions. I've seen that this one is something that sometimes scares students for no reason. So it's just about looking at simple ways of going about certain derivations, because it's not all equations where you are asked to derive expressions, but you can see it can come in an exam. So it's always good when you encounter a new expression in physics, you should know how it is derived. Rather than just memorizing an equation, you should know how it is derived. Let's look at question 16b. We are given that a pendulum bulb of mass 20 grams is whirled in a circular path of radius 100 centimeters, that is 1 meter, at a velocity of 0.5 meters per second. Determine the centripetal acceleration of the bulb. Of course, it's here, we just need to remember that since we know the speed, the linear speed along the circular path, the speed along the circular path is just a matter of remembering that centripetal acceleration is given by v squared over r. So we just need to substitute v squared over r, and we get the acceleration to be 0.25 meters per second squared. Okay. Then when it comes to calculating force, centripetal force, remember this centripetal force is a resultant force, and resultant force is given by ma, and we already have a and we have the m somewhere around here. So by using F is equal to ma, F is equals to ma, where m is 0.02 kilograms, and the a, we already have it, it's this much, we get a force of 0.005 newtons. That is the centripetal force. C. Explain why a car should reduce its speed when negotiating a sharp corner. Why should a car reduce its speed. We must remember that the centripetal force on the car is provided by the sideways frictional force between the surface of the tire and the surface of the road. Okay, so it is important that the centripetal force on the car should be less than that frictional force. Okay, it should be less than, because if it is the centripetal force required by this car to move around that circular track is more than the frictional force, then the car is going to skid and probably move into a ditch. Okay, so the centripetal force on the car should be less than the sideways friction force between the surface of the tire and that of the road surface. That frictional force, that centripetal force, should be less than the frictional force. That's why we should reduce the speed in order to reduce the centripetal force, so that it is always less than the friction force. This is in case where the centripetal force is provided by the friction, only by the friction force. Okay, only by the friction force. So in many corners you find that the roads are banked, but in this question that knowledge has not been provided, so we cannot rely on the horizontal component of the weight of the car to provide part of the centripetal force. All the centripetal force is provided by the friction force. What would happen if the tires of the car are slightly worn out? That's why we must reduce the speed when negotiating a corner, especially where the surface is horizontal, where the surface is flat. Question 18. State Archimedes' principle. This one is direct for 1 mark. It's probably something that you would want to remember, that you can be asked to state a law, you can be asked to state a principle, you can be asked to describe it. Let's see how Archimedes' principle is stated. When a body is wholly or partially immersed in a fluid, so it works if the body is completely immersed or partially immersed. Immersed in a fluid, not a liquid. I'm sure Marcus will be looking at this. If a student talks about a liquid, then you lose this 1 mark, because laws are supposed to be as general as possible. They apply to both gases and liquids. Other students will state water. Don't state water here. You may have used water to verify Archimedes' principle, but it works. Whether it's water, paraffin, glycerin, any other liquid, or even gases. So be careful. It is a fluid. So when a body is wholly or partially immersed in a fluid, what does it do? It experiences an upward force or an upthrust, which is equal to the weight of the fluid displaced. What are the mistakes that students make when they are stating Archimedes' principle? Other than confusing fluids with the liquids or water or any other term here, it should always be fluid. They also make this other mistake. They say it is equal to the mass of the fluid displaced. It's equal to the volume of the fluid displaced. It's equal to the, sometimes students don't even mention which physical quantity it is equal to. It is equal to the fluid displaced. All those statements are wrong. It should be, it is equal to the weight of the fluid which is displaced. Very important. So learn to state laws or principles as completely as possible as they are stated in your course book. So let us look at part B of question 18. To verify Archimedes' principle, a student is provided with water in a measuring cylinder, a solid metal, a piece of thread, and a spring balance. right? Describe how, 1, the mass of water displaced may be measured using these apparatus. We are not required to use any other apparatus other than this. And the only way we can do this in order to measure the mass of the water displaced is first of all to determine the volume of the water displaced and then use the density of water to calculate the mass of the water. All right? So how do we do this? These are the steps that we are going to follow. Number 1, note the volume of water in the measuring cylinder, maybe call it V1. 2, suspend the solid using the piece of thread and immerse it in the measuring cylinder until it is completely immersed. When that happens, you note the new volume of water, call it V2. The volume of water displaced will be V2 minus V1, and then mass of water is calculated by multiplying the density of water by that volume, by the volume of the water displaced. So this is how we can determine the mass of water displaced. So let's go to the next part of the question where we are asked to Archimedes' principle may be verified, where we are asked to show how Archimedes' principle is verified. All right? So what do we need here? We needed to measure the upthrust on that solid. We measure its weight in air, weight in water, and then find the difference. That will allow us to find the upthrust. And then, remember, we already know the mass of the water from the previous part. We know the mass of the water. We can calculate the weight of this water displaced. Since we know its mass, we can calculate the weight of the water displaced. So we are going to compare that upthrust with the weight of the water displaced. So let's see how you would probably list these steps. So what are the steps? Use the spring balance to determine the weight of the solid in air. Call it W1. And notice that when I'm describing how a given physical quantity is measured, I'm also mentioning the measuring instrument. So here we are using a spring balance to determine the weight of the solid in air. All right? What next? While still suspended from the spring balance, completely immerse it in water. But it should not make contact with the bottom of the measuring cylinder. Okay? It will be fully immersed, but don't allow it to touch the bottom of the measuring cylinder. So observe that one very carefully. Next, so you should ensure that this solid does not touch the bottom of the container. Okay? And then determine the reading of the spring balance, W2. This is the weight of the object or the weight of the solid when immersed in the liquid. It is its apparent weight. This is its weight in air, or its actual weight. The difference between the two will give you the upthrust on the solid. So the upthrust U is given by W1 minus W2. Then calculate the weight of water displaced. This one is a calculation. Weight of water displaced. Remember from the last section, section 1, we were able to determine the mass of the water displaced. So here we calculate the weight of water displaced. And then now we compare the upthrust and the weight of the water displaced. And they should be the same. Upthrust is equals to weight of water displaced. And that is how you will verify Archimedes' principle. So remember, in such steps, your descriptions must be as complete as possible, as clear as possible, and where necessary, state any precautions that you are supposed to take. In this case, one precaution is the object should be completely immersed And even if it is completely immersed, be careful, it should not touch the bottom of the measuring cylinder. State one way of reducing the surface tension in liquids. Of course, one of the ways of reducing the surface tension is to raise its temperature or put impurities in it. It's just one way which has been asked. So you can say raise its temperature or put impurities in it. Let's go to question or to part 2 of that question. Part 2. It is observed that when a certain object is placed in water, it gets fully immersed. However, when the same object is placed in glycerin, it is partially submerged, as shown in figure 7. Okay? When it is in water, it is completely submerged and probably supported by a piece of thread. But when it is in glycerin, it floats. Okay? In such a case, you might not even need this thread, but it is floating. Okay? You're asked to explain this observation. Okay? Here, it is completely immersed. Here, it is partially immersed. So the volume of the water displaced is more than the volume of the glycerin displaced. So there we cannot compare the two because the two volumes are different. But we know each one of them experiences an upward force according to Archimedes' principle. When an object is wholly immersed or partially immersed, it must experience an upward force on it. So there is upthrust on the object due to the water. There is upthrust on the object due to glycerin. This question is about an application of Archimedes' principle, right? Because first of all, the object here is completely immersed. Here it is partially immersed. Here it sinks in this liquid. Here it floats in the liquid. Here the density of this liquid is different from the density of this liquid. So all these factors must be put into consideration when you're trying to explain why this happens. Okay? So number one, there is upthrust in both of them. Okay? So first of all, we would want to fully submerge this object in water as it is completely submerged, and also submerge this object in glycerin. What we are going to discover is that the volume of water displaced is equal to the volume of the glycerin displaced if both objects, if the object is fully immersed in water and in glycerin. All right? The volumes are going to be the same. But the upthrust here would be greater than the upthrust here because the density of glycerin is larger. Next, the weight, the upthrust here is less than the weight of the object in air. That's where that object sinks. Over here, the upthrust on this object would be greater than the weight of the object, and that is why it floats. Okay? It is pushed upwards because the upthrust will be greater than the weight of the object. So the moment it moves above the surface of glycerin, less volume is going to be displaced. Less volume of glycerin is going to be displaced. That will have the effect of reducing the upthrust force on this object until the upthrust is equal to the weight of the object. The upthrust will be equal to the weight of the object. All right? And since upthrust is calculated as the volume of the object times the acceleration due to gravity times the density of the liquid, so when the volume is reduced, then the upthrust is going to be reduced. Those are some of the points which you must mention between this diagram and this diagram, because there are so many factors to consider What are these different factors? Factor number 1, the two liquids have got different densities. Factor number 2, over here it is wholly immersed, here it is partially immersed. What is the other factor? Here it is floating, here it is not floating. It is fully submerged and therefore probably supported. Those are the three factors which you must be able to consider as you look at the reason why this is the case. Different densities, different volumes of liquid displaced, floating, here it is sinking, but the weight of the object in air remains the same. The weight of the object in air remains the same. So by looking at the points that I've written down here, probably you can be able to figure out an explanation for this observation. But this is one of those questions which was very challenging according to me. But for you to get these 3 marks, you have to mention a number of points. So let's look at question 19. Question 19, what does it state? A stone and a piece of paper are released from the same height in a vacuum. It is observed that they both hit the ground at the same time. Explain this observation. Explain this observation. So they are subjected to the same acceleration due to gravity of 10 meters per second squared, which is independent of the size or mass or volume of the object. So this is motion and gravity. Any object of any mass or any volume, provided air resistance is neglected, will have the same acceleration, which is acceleration due to gravity, and it has a value of 10 meters per second squared. The next question, we are told that a car of mass 1560 kilograms traveling at a velocity of 25 meters per second is brought to rest by a constant force of 3,000 newtons. Okay. Part 1. Determine the change in momentum of the car. Of course, change in momentum is mass times change in velocity. And you can see the velocity changes from 25 meters per second to 0 because it is brought to rest. Final velocity is 0, initial velocity is 25 meters per second, and this is the mass. So probably we can use this equation here to calculate the change in momentum. Change in momentum is mass times change in velocity, and when we substitute, we get the change in momentum to be negative 39,000 newton seconds, or kilograms meter per second. All right, the negative sign indicates that that change is a decrease in momentum. Part 2, we are asked to calculate the time it takes for the car to come to rest. Of course, we know that change in momentum is equals to force times time, so we can divide that change in momentum by the force to get the time. We got that impulse equals change in momentum, and we have change in momentum, and we've got the force. So to get time, we just need to do this subdivision, and we get 13 seconds. This is supposed to be 13 seconds, not 3 seconds. 13 seconds. C. Jane measured the length of the palm of her hands as 18.7 centimeters. Describe how the palm length may be used to estimate the length of a laboratory tabletop. So, this is what she's going to do. She's going to determine the number of palm lengths and multiply it by the length of her palm. That is what she will do. Part 2 of that, we are asked, explain why estimated that the length of the table top in 1 is not accurate. Of course, it will not be accurate for several reasons. The palm may not have may not have been in a straight line. Had she laid her hands along the table, she may not have done that in a straight line. You know, there might have been a bit of crookedness along the line, making it longer than the actual length. Okay? What is the other error here? There might be space between the palms, or even the palms may have overlapped. The palms also may not be of the same length. All these are some of the errors which might have reduced the accuracy of the measurement taken using the palm length. And that is how, in my own opinion, you would have answered this paper. If you're preparing for maybe for examinations in 2026, this paper would be quite useful. Like I told you, I've prepared a document which makes it very easy for you to revise this particular paper. For example, if you hover your cursor over any of the questions, it gives you the topic from which that question is set. You can see that. As I do that, the topic keeps popping up. So if you are revising using this document, and probably you are using a computer, you can download this document and be able to access this. So if you want to revise maybe topics such as this, which is measurement 1 or measurement 2, just do that, and it's going to, the moment you click, it gives you the question which is being tested. For example, this one would be in a certain topic. You click on it and you find that you're going to revise that particular topic. So that is how you would answer the questions in that paper. Bye-bye.